Function or not a function? Why not? What is that again? Loud, please. I can hear. It doesn't pass the vertical line test, right? So that's correct. The vertical line crosses more than once, and well, so that's not a function. That's essentially telling us that, for example, if this is a function of position versus time, that will mean in a way that we are in two different places at the same time, which is weird, isn't it? So, well. What if I told you that this can be a function if we define it in a different way, you know? And in fact, well, if we define it in parametric form, this would be a function because in this case, this path right here represents the motion of a particle at different times, right? And actually, this is going to have some sense of direction as opposed to the graphs of the usual functions that we are used to graph that do not have a sense of direction. You know, we can just what we did back in graphing the other kinds of functions, just make a table of values and plug in the points, but we never got an instruction like you have to do it following this order. You know, you can plot whatever point related to x equals 1, then the point x equals 3, and then go back to, I don't know, the point related to x equals -5. So we're not following an order. In this case, we kind of are following an order, and the fact that we're following an order, that gives us some sense of direction for a particle. And well, in this case, if you consider a particle moving, you know, along this path, this particle is never in more than one place at the same time, you know, and you can relate this to, you know, to those military aircraft. I don't know if you've been to the Miramar Air Show where they do these pretty cool maneuvers. They do this kind of sideways parabolic motions, and well, an airplane, well, is never in two different places at the same time. For example, at t equals 0 seconds is here, t equals 1 second, t equals 2 seconds, t equals 3 seconds, 4 seconds, etc. All right? So, and in a more generalized way, maybe when you read maps, you know, whether maps in paper or in Google Maps, and you're looking for directions to go from point A to B, you very oftentimes you would see or rather a path like this to take you from point A to point B based on the most efficient route, based on where there's a lot of traffic or where there's less traffic, you know. And well, and again, if you look at those paths on Google Maps or on a paper map, well, try to do the vertical line test, it's going to fail it, right? Because it crosses more at more than one point. And well, but again, in this case, we have a sense of direction after 1 minute, after 2 minutes, after 3 minutes, after 4 minutes, etc. Right? And well, your drive is not going to be in two different places at the same time. It's just following a path. Now, how do they look like? So these kind of equations are going to look like a system of equations containing, well, for now, for Calc 2, it's going to be two equations. In Calc 3, you're going to look at the three-dimensional case in which you will represent lines and other curves in space, right? For now, we're going to look at this in the plane. And both of these functions, x and y, are going to be functions of a new variable in the background, so that is a function of time. They're both functions of time. All right, so let's have a look at one example. How do we graph them, and how do we identify what graph is this doing? In other words, what we have to do here is to eliminate the parameter. All right, so we're going to eliminate the parameter, to identify what graph, because I mean at first glance, well, it's not that obvious about what it is really, but we can get an idea by well, after we look at some of this, we may get an idea of what are we really graphing here. Well, so we're gonna make a table. So, well, back when we were graphing rectangular function, that's how we call these functions, f of x equals y, either rectangular functions or Cartesian functions, because we were graphing in the Cartesian plane. Well, technically we're still graphing in the Cartesian plane, however, we're introducing a third-party variable in this case, and this third-party variable, t, which is time, typically represents time, is controlling x and y. So for different values of t, we will be having different order pairs again. So at different times, a particle is at a different point, at a different order pair, or a different position, if you will. All right? And so all we have to do is simply plug in t on both equations. In this case, plug in t equals 0 for the x equation. That's going to be 0 squared minus 2 times 0, which is just going to be 0. For the y component, that's a 0 plus 1, which is 1. And this will produce the following order pair. That's the order pair 0, comma 1. So that means that at t equals 0, the particle is located at the point 0, comma 1. All right, so what about t equals to 1? So when t equals to 1, that is t squared, which is 1 squared, which equals 1, minus 2 times 1, that's 1 minus 2, that's negative 1. And plug it in the y equation, 1 plus 1 equals to 2, that produces the order pair, negative 1, comma 2. For t equals to 2, do the same. 2 squared, which is equal to 4, minus 2 times 2, which is also 4. We get a 0 for the x component, and 2 plus 1, that's a 3. Producing the order pair, 0, comma 3. And let's keep going with the other three values of t. So that's going to be 3 squared, which is 9, minus 2 times 3, which is 6. 9 minus 6, that's a 3. And 3 plus 1, that's a 4. That produces the order pair 3, comma 4. And last but not least, 4 squared, which is 16, minus 2 times 4, which is 8. 16 minus 8, that's an 8. And for the second equation, the y equation, this is 4 plus 1, which equals to 5. All right? So that produces the order pair 8, comma 5. And well, so how about we plot these points? Maybe here. I'm going to need some space. All right. So that's 1, 2, 3, 4, 5. Let's scale it. 1, 2, 3. All right. So let's plot these points. Let's plot the point 0, 1, which corresponds to the first order pair, that is to t equals to 0, the point negative 1, comma 2, and the point 0, comma 3, the point 3, or is it a 3? Yes, 3, comma 4, so that's 1, 2, 3, 4, and the point 8, comma 5, so that's 3, 4, 5, 6, 7, 8. So it's going to look like this. And let's connect the dots. And it's going to look sort of a sideways parabola here, all right? However, there's more than we need to plug in here, all right? What is that? So number one, we need to label this. We need to label each point to its corresponding value of t. That is, t equals to 0, t equals to 1, t equals to 2, t equals to 3, and t equals to 4. Well, because of this, this is following certain direction. It's going in this direction. That's how the particle is moving. So, as you can see, in comparison with the graph that we have been doing before parametric, well, yes, we graph them the same way by plotting order pairs. That doesn't change. However, those order pairs are not, for those order pairs, we don't have a y depending on x as we did before. In this case, it's both x and y depending on a new variable t, which is time, which is the different times at which the particle is moving. We can generalize it as position versus time. Of course, there's other parameters that you're going to learn in Calculus 3, such as the arc length parameter, instead of looking at the position of a particle after 5 seconds. Well, you will be looking at the position of a particle after an arc length, or rather a distance of 5, a distance of 10, different parameters. So, but for now, we start with the easiest of the parameters, which is t, which is related to time. Well, they're also asking us to eliminate the parameter, right? Well, in order to eliminate the parameter, go with the easiest equation and solve for t. Well, in this case, the easiest of the equations is the second one, because we can just subtract 1 from both sides to leave the t by itself. That means if y equals to t plus 1, that means t equals to y minus 1. What are we going to do with this t equals y minus 1? We're going to substitute back in the first equation wherever we see the letter t. All right, so that's x equals to t squared minus 2t. So all we do is plug in t equals y minus 1 over here, over there, and x equals to y minus 1 squared minus 2 times y minus 1. And well, that essentially looks like the equation of the parabola. However, let's expand the binomial here and distribute the negative 2. That's y squared minus 2y plus 1 minus 2y plus 2. Simplify, or rather collect like terms, combine like terms. That should give us x equals y squared minus 4y and plus 3, which is indeed the equation of a parabola. It's a quadratic function. However, it's a function of y, not the usual function of x, which otherwise would have described a parabola opening up or down depending on the sign of the leading coefficient. In this case, it's a positive leading coefficient for y. That means it opens to the right. All right. So that's one example of what parametric equations look like. What else? What's the difference? How are they related with the usual functions that we graph? Of course. All right. And well, let's name the conic section here that we relate. So this is a parabola. Okay. So there's a bunch that we can do with parametric equations. Well, let's look at a different case. So, for example number 2, what curve is being represented by the following parametric equations? X equals cosine t plus e, and y equals to sine t. Well, so in this case, we cannot just solve for t and plug it in the other equation. We would be in trouble because, for example, if we get this t equals arc cos of x, and then try to plug it in here, that would have been y equals sine of arc cos of x, which is kind of a weird function to describe. So when it comes to parametric equations involving trigonometric functions, that's not how we're going to do it. Well, actually, there's a little hint here. Something varying between 0 and 2 pi. Can anyone think of something varying between 0 and 2 pi? What is that? Let's say it's a circle. Yes, it's a circle. But I mean, how are we going to go from x equals cosine t to y equals sine t? Well, yes, I mean, depending on the different, we can parameterize this over different ranges. However, the 0 to 2 pi is just to write it in a general way. So, well, how are we going to, you know, eliminate the parameter to identify the equation that this is representing? Well, so number one, if we write down the equation of the unit circle, x squared plus y squared equals to 1, well, we can easily relate it to this because, well, if x is cosine, this is cosine t, quantity squared plus sine t, quantity squared equals to 1, that's cosine squared t plus sine squared t, which equals to 1. All right? And well, isn't that an identity? Cosine squared plus sine squared equals to 1. So in this case, we take advantage of the Pythagorean identity in order to go back and forth between parametric and rectangular for a circular. And by the way, how do we know this is the unit circle? Well, that has to do with the coefficient here that we have in front of the cosine and the sine. We're going to look at this more in detail as we move on through the next examples. However, yes, okay. So, indeed, this is a circle. This is a circle. But how do we know about the orientation? Because, I mean, these are parametric equations, and these parametric equations describe the motion of a particle on a curve. And in this case, there's two possibilities for a particle to move along the circle. Number one, either it could be clockwise or it could be counterclockwise. How do we know about that? Well, so if we go to our graphing calculator, so we might want to go to the mode where it's parametric. Make sure parametric mode is highlighted, and well, because we're dealing with trigonometric functions, it's important to make sure that we also have the radian mode. All right, so when we plot the functions here, let me clear this. As opposed to graphing regular functions of x, and usually we will have y1, y2, y3. In this case, we have pairs of equations because we're going to have an equation for x and another equation for y. So all we're going to do here is type the equation for x, which in this case is cosine of t, close parentheses, and sine t. Okay? And okay, so by the way, be careful when you're graphing parametric equations using a graphing calculator. Be sure not to blink when you click graph, because sometimes graphs are plotted so quickly that you would miss the direction in which it's going to be plotted. So let's see what we get here. Okay, that was like too fast. I was barely able to see the direction. So if it's too quick, let me give you an advice here what to do. So go to Window and ask the parameter t to draw more points. In this case, I'm going to make the step that is the number of points that the graphing calculator is going to plot. Instead of 0.1, I'm going to go with 0.01. That's going to take longer to draw because it's going to draw more points. And let's see what happens. Well, much better, isn't it? Quicker. So in this case, it's going counterclockwise in this case. All right. Well, can we relate this to anything we have done before? I mean, think of trigonometry, your basic trigonometry. Aren't these ordered pairs of the form cosine, sine? And in this case, we go counterclockwise with the angles, 0 radians, pi over 2 radians, pi radians, and so on. All right. So in this case, that's going to give us the sense of direction for the unit circle. All right. Well, so what about other cases? How do we make a circle? In this case, go the other way around, go in the clockwise direction. Well, that's the next example. All right, so let's see. What curve is represented by the following parametric equations? And what do we have this time? Sine of 2t, cosine 2t. Well, in this case, the difference with respect to the other example, we have the equations reversed. So number one, let's eliminate the parameter, again, using the equation of the circle, which happens to be x squared plus y squared equals 1. In this case, well, let's call it a unit circle for now. And, well, so that's going to be, what is this? Sine 2t, quantity squared, plus cosine 2t, quantity squared, equals to 1. Well, that's the same as saying sine squared of 2t plus cosine squared of 2t. And again, this is the Pythagorean identity. Recall that identities work for every multiple angle, you know, the usual. So sine squared x plus cosine squared x equals 1. It still holds if you have a sine squared of 5x plus cosine squared of 5x. It works as long as the multiple angle is the same, and it's the same for every other identity. You know, like the reciprocal identities, they work the same. Just do it with the same, as long as it works with all of them having the same angle. All right, and well, that's again the equation of a circle. However, let's see. You know, okay, let me focus here about let me do this for the previous example. I think I forgot to do this on the previous example. So this is the graph in parametric form. Let's also draw the graph in rectangular form. Well, we all know how the graph of sine looks like, right? I think it's a very straightforward one. You know, it looks like this. It starts at the origin and completes one cycle from 0 to 2 pi. That's 0, 2 pi, and of course, if you want to calculate the period, just to make sure, p is 2 pi divided by the quantity b, where b is the coefficient in front of the variable b, which happens to be 2 pi over 1, which is 2 pi. So that's why the period for the function of y equals sine is 2 pi. It's going to make a difference. It's going to be a little different when it comes to the next example. So, number one, let's calculate the period 2 pi over b, which is 2 pi over 2. This time we have a coefficient of 2. That means the period will be pi. Okay? Well, how is this going to be a difference when it comes to graphing the function? Well, first of all, I'm going to graph the rectangular version, then I'm going to go to the parametric form. So number one, so that means that the graph of y equals cosine 2t completes one cycle after pi, all right? However, okay, check this out. So that's 1 pi. However, the condition for this parametric equation is that we still graph between 0 and 2 pi. That means that the graph will complete instead 2 cycles. All right, that's 0, pi, 2 pi. All right. How is that going to be represented when we graph it in parametric form? All right, let me go to the graphing calculator. So that's y equals to, okay, let me clear everything here because everything is going to be reversed. So that's sine of 2t, close parentheses, cosine 2t. Okay, so let's graph. Okay, this was a little hard to see, but actually the parametric graph actually did two turns in the clockwise direction. Let me see if I can zoom it in. Just zoom in. Do you see that it's kind of doing a second turn? It's kind of hard to see. Were you guys able to see that? Well, that's what it's doing in the background. So it's, in this case, it will be the graph of the unit. It's a unit circle still. However, in the clockwise direction, and note it's traversed twice, as opposed to the previous example in which the graph was traversed once. Question: how do we have to design our set of parametric equations if we want circular motion in which a particle traverses 5 times? What do we have to modify in our parametric equations? Any ideas? For a 5, all right? So that multiple right here tells us essentially the frequency, if we will, in the interval 2 pi. In this case, is twice. The frequency is 2 because it completes 2 cycles in this case, okay? All right, let's have a look at another example dealing with circles. So notice the coefficient 2, for example, number 4. The coefficient 2 is no longer inside of the angle of the trigonometric functions this time. It's rather in front of the trigonometric functions, well, which originally, this one right here, would be, that's the amplitude actually. That coefficient in front of the trigonometric function, it's a vertical stretching factor, like in a generalized way to describe all the shiftings and transformations. And well, in this case, this will make the sine function to go between -2 and +2, as opposed to -1 and 1. Well, so that's the amplitude. What's going to be the effect in its parametric form? So number 1, well, this time we're gonna do a little bit more of work in order to describe its corresponding rectangular equation. So number 1, I'm going to start with x equals to 2 cosine t and y equals to sine t. I'm going to solve for the trigonometric functions on both cases. That is, cosine t equals to x over 2 and sine t equals to y over 2. So we are safe now to go about the trigonometric identity. That is, cosine squared t plus sine squared t, which equals to 1. So that's the Pythagorean identity to go back from the world of parametrics to the world of Cartesians, And well, so this is the same as saying cosine t quantity squared plus sine t quantity squared equals to 1. Well, all we have to do here is the following. Substitute cosine t equals x squared, which is this quantity here, and sine t equals y over 2 over here. Well, that's going to make it an x squared. First of all, x over 2 quantity squared plus y over 2 quantity squared equals to 1. Of course, we have to do a little bit more of work in here. So that is square x squared over 4 plus y squared over 4 equals to 1. And we're almost there to get the actual equation that it's represented in the world of Cartesian. That is, multiply both sides by 4, x squared plus y squared equals to 4. And well, can we identify what x squared plus y squared equals 4 describes in Cartesian? So what it is? It's a circle of radius, not 4. Well, 4, this number 4 is the radius squared, so circle of radius 2, right? Does that match with the amplitude 2 from the Cartesian version of just sine? Well, that's a big connection, right? So this will be a circle, not of radius 1. It's not the unit circle anymore. It's a circle of radius 2, negative 2 to 2, negative 2 to 2. Now, without graphing this using the graphing calculator, which direction is this going to take? Is it going to take the clockwise direction or the counterclockwise direction? Counterclockwise, how do we know it's counterclockwise? The x is cosine, right? That's one way to, to relate to relate which direction is this going to go. Because notice it's like the previous example. Example number 3 had the x to be the sine and y to be cos, and the equations, or rather the functions, were reversed. And in that case, that's the reason why it went in the opposite direction, in the clockwise direction. However, for this example, which again we go back to cosine and then sine, that takes us back to what's this? To counterclockwise direction. And you know what? Let's plot them, just so you can see the difference. So that's going to be so that's 2 cosine t and 2 sine t. All right. Let's click graph. You see how it goes this time in a counterclockwise direction, right? And well, of course, because of the aspect ratio of the screen on the graphing calculator, it's not going to look circular. It's going to look like an ellipse, but it's not an ellipse, okay? So that's usually a downside when using the TI calculator. Just make sure that to understand that this is, yes, it's indeed a circle, even though it looks elliptic. Let's look at one more example. So find the parametric equations for the circle with center HK and radius R. That is a generalized way to parameterize a circle. And well, in this case, we are going to do the counterclockwise version. Counterclockwise orientation. So we're going to start with the equation, with the general equation for the circle. That is x minus h squared plus y minus k, quantity squared, equals to r squared. So that's the equation of a circle in general form, centered at hk and having a radius r, which gets squared upon writing it in the equation. Well, so the number one thing we want to do in this case is divide both sides by r squared. Because we want a number 1 on the right hand side, because since we will relate this equation to the Pythagorean identity, sine squared plus cosine squared, or the reverse, we want to make sure that we have a 1 on the right hand side. So that's the trick. And well, we have a square over something squared. Well, how about write everything x minus h over r, quantity squared, plus, and the same, y minus k over r, quantity squared, and this equals to 1. So x is cosine t and y equals sine t. That is, we can relate a couple of equations here. We can go about cosine t equals x minus h over r, and sine t equals y minus k over r. So solving for x and y respectively, okay, multiply both sides by r, that's x minus h equals r cosine t, and x equals r cosine t plus h. On the other hand, y minus k equals r sine t, and y equals r sine t plus k. And well, this is going to explain why these coefficients in front of the functions cosine and sine in the set of parametric equations have an effect on the radius, on having not a sphere, I was going to say a sphere, a circle of a larger radius. You know, like in the previous example, we had a coefficient 2 in front of the function that had an effect of making a bigger circle, in this case a circle of radius 2. And well, putting all this together in the form of a set of parametric equations, that should look like x of t equals r cosine t plus h, and y of t equals r sine t plus h. And of course, let's just draw a very generic graph. I mean, it can be anywhere, because the center can be anything. That HK can be anything. It doesn't have anything to do with the direction. So the center of the circle, it doesn't have anything to do with the direction. All that it dictates the direction is the order in which we write the parametric equation. So that is, we can just draw a circle anywhere that is the center HK, the center is at HK, and it has a radius R, and most importantly is oriented counterclockwise. All right? Yes. Which one? Which square?
The variable was so we're replacing cosine.
Oh, because this is really the same as saying cosine quantity squared, so whatever is inside is just going to be cosine without the squares.
Oh.
Yeah. And this is in general the equation of a circle, this time to having all its properties, other radii and center at the origin. So for the previous couple of examples, we went just with the very basic examples in which it was center at the origin and the like. For example, let me make something up over here. So let me go to the graphing calculator. Let me clear the first set of equations. Let me do a circle of radius 3, for example. But in this case, I'm going to shift this to have an h at, I'm going to say, plus 2 and plus 1. Let's see what happens if it's shifted correctly. Well, we may not be able to see the whole picture. Well, let's zoom. Well, it's going to take a minute. For whatever reason it's thinking. Oh yes. Zoom standard. And well, notice it's shifted. It's no longer centered at the origin, right? And again, it was traversed only once, and it went counterclockwise. If we wanted to go clockwise, we just reverse the order of the equations. All right?